So now we're going to look at cache blocks or cache lines. And this is a more efficient way for storing data in the cache by storing it in larger chunks. So before we get to that, let's look at how efficient our cache design is. So we're going to look at two things, and the first is searching the cache. So what do we need to do to search the cache to see if our data is in there? Well, we could search each entry in the cache one at a time. This will take n cycles for an n cycle cache. You can search the first one, the second one, the third one, the fourth one, and the fifth one to see if the data is there. Or we could search them all at once. And since we want our cache to be fast, we'd better search them all at once. We can't afford to wait 100 cycles to search 100 entries in a cache because we might as well just go to the main memory. So if we want to search them all at once, what do we need to do? Well, we need to have the address, so we can compare the tag. And then for each entry, we need a comparator to compare the tag with the address, and an AND gate to see if the valid bit is set. And then we have to do this for every entry in the cache. So we need a lot of comparators and a lot of AND gates. So this is too expensive. If we have a 100 entry cache, we can't build 100 comparators to search the whole thing at once. How about the memory usage of the cache? How efficient is that? Well, we have 32 bits for our data, we have 1 bit for our valid, and how many bits do we need for the address tag? Well, we need 30 bits for the address tag, and that's because the last 2 bits tell us which byte in the word. So we have the whole word in the cache, so we don't need the last 2 bits to identify it because the bytes are within the word. They're not that word's memory location. So we need 30 bits for the address tag. So we've got 32 bits for the data, 30 bits for the tag, 1 bit for the valid, so 63 bits of data for each entry into our cache, but only 32 of those bits are storing data. So half of our size of our cache is actually storing useful data. And this is also too inefficient. So let's see if we can fix that. So the problem we had was too much space for tags. We identified another problem, which is too much logic. We'll deal with that one later. So now let's fix the space issue. So if we have 1 word per tag, we waste 1/2 of the cache. Well, if 1 word wastes 1/2, how about 2 words per tag? So in 2 words per tag, now we're just going to waste 1/3 of the cache. Well, okay, let's try more. So 4 words per tag, we'll just waste 1/5. 8 words per tag, we'll just waste 1/9. All the way up to 16 words per tag, we'll only waste 1/17. And this is what processors do today. So what did we do here? Well, we used larger blocks of data in the cache, and we need 1 tag for every block. So if we have a larger block of data, we have fewer tags for all the words, because we just have 1 tag per block, so we get more efficient storage. So this chunk of data here, or this block, is known as a cache block or a cache line. This is the element of data that we store in the cache. So how do we access data from a cache if we have multiple words in every cache block? Well, it's pretty much the same as before. We're going to check the tag, see if it's in the cache, we're going to check if the valid bit is set, and then we're going to read the data from the cache. However, we have multiple words in each cache block, so we need to get out the right word. To do that, we're going to put in a mux. So when we access a cache block, we're going to get out data from multiple words. We can then use a mux, and this mux is going to determine which data we send back to the CPU. Now, how do we choose which entry into the mux? Well, for that, we use the address. So let's take a look at some addresses, look at what tag they have for the block, what tag they have for which word in the cache, and for the byte. So address 0 is going to go into block tag 0, and that's word 0. So that's over here, address 0. Address 4 is going to be in the same block as address 0, but it's going to be in the other word. So the address is going to be is over here. So for this, we're going to have the mux set to choose the other data. 8 now has block tag 1. So this is going to go in the second block in the cache, in the first word, and address C is going to have the same block tag 1, but is going to have the other word. So we can see that this bit here, these word bits, are the ones we use to choose which word of data we take out of the cache line. And we also see that the tag here is only going to look at some of the bits. It's not going to look at all of them the way it did in the previous cache. So we're going to take the tag bits, those are the ones that don't determine the word and don't determine the byte, and use those to search for the tag. That's why the tag for the second line in the cache is 1 and not 8 the way it was in the previous example. So let's take a look at the address bits. So here we've got a cache which has a single word in each line or each block. And here we've got two other caches which have 2 words per block or 4 words per block. So for the 1-word cache block, here's how we're going to use our address bits. We're going to use 30 bits for the tag and 2 bits to determine which byte in the 32-bit word. For the 2-word cache block, we're going to use 29 bits for the tag, 1 bit to choose between the 2 words in the cache line, and 2 bits to choose which byte we want in that word. Similarly, for a 4-word cache block, we're going to have 28 bits for the tag. Now we have 2 bits to choose between the 4 words, and we have 2 bits to choose the byte in each word. So the last 2 address bits are going to determine the byte within the word. The next n are going to determine which word in the cache block, and n is a function of how many words we have per cache block. And the remaining bits, those are going to be used for the tag. So those are the bits that are different for every memory address, and we need them to do the unique identification. So let's take a look at an example here. We're going to go through the same instruction memory, but now we're going to compare it across a cache with 1 word per block, 2 words per block, and 4 words per block. So for the first instruction, all of the caches are going to have to fetch data because they don't have any data. The 1 word per block cache is going to fetch 1 instruction. The 2 word per block cache is going to fetch 2 instructions, and the 4 word per block is going to fetch 4 instructions. Now when we go ahead and execute the next instruction, the 1 word per block cache is going to have to fetch again because it doesn't have the instruction in the cache. But both of the other caches already have that instruction, so they don't need to do a fetch. For the next instruction, we go back to add I, and all of the caches have that. And then we go to branch not equal, and again, all of the caches have it. But now we go on to the add instruction. And now here, the 1 word and 2 word per block caches are going to have to fetch the data because they don't have it. But the 4 word per block cache already does have it. Then finally we go on to jump, and the 1 word per block cache is going to have to fetch that, whereas the other 2 already have the instruction. And at this point, all of the caches have all of the instructions, so they can just execute. So why does the 4-word block size work so much better than the other ones? Well, the reason for this is it loads data we'll need later. So the 4-word one got lucky. It loaded the instruction we wanted plus the next 3 instructions. And it turns out that we're very likely to use the data after the data we load. This is called spatial locality. We're very likely to use data near the data that we access. So by loading 4 words at a time, the larger block size has effectively gone and pre-fetched or gotten the data we need in the future ahead of time. So this is why we use larger cache lines, because this prefetching, this ability to go get data that's near the data we want, makes it very likely that we'll already have the data that we need in the future. So let's take a look at larger cache blocks. What are the benefits? Well, we waste less space on tags. We have a higher percentage of data because we need 1 tag per block, not 1 tag per word. And we get this great spatial locality. So we're loading the next bunch of words and we'll very often use them, which will speed up performance. But there's some downsides. If we don't use all the data in the cache block, we're going to waste space. So for example, here's 2 cache blocks with 4 words each. And you can see they have an array, A0 through A7. Imagine we have code that looks like this. We're walking through the array, but we're walking through it by incrementing by 2 every time. So this is the pattern in which we're going to access the data. What you can see by this is by having a large cache line, we've wasted half the space in the cache. If we had a smaller cache line, we wouldn't have loaded every other element, and we might have wasted less space. So what happens in the real world? Well, almost everything today has 64 bytes as the standard cache line size. In fact, if you're on an Intel machine, you always get 2 cache lines every time you fetch 1. So every time you ask for 1 word of data, you're getting 15 other words at the same time.